Hey, what's up, gang? I'm here. I'm gonna attempt to explain to you the photoelectric effect. So we'll see how I do. I tried kind of jotting some things down on some paper, and I'll use some graphs and some visuals. So hopefully you'll be able to learn something from this video. Thanks. Okay, I'm kind of challenging myself here. I'm seeing if I can explain the photoelectric effect to you in like 45 seconds. So I'm going to start here at 10 seconds. Boom, now. Okay, so the photoelectric effect involves, there's three keywords in there: photo, electric, and effect. Photo, that relates to photons, light. Electric, that involves electricity, electrons, okay? So we've got light, we've got electrons, and then effect. The effect is just what we see happening, okay? So basically, Albert Einstein was one of the main guys who used this effect or this experiment to try to find out what light is about. He really helped. Previously, it was thought that that light only traveled as a wave, but it was light actually travels as a particle as well, and the photoelectric effect is a huge part in showing that. So basically what happens, light shines on a metal and an electron is emitted from that metal, and from that we learn a whole bunch of really cool things about light. And that's my over 45 seconds on the photoelectric effect. Okay, so what is the photoelectric effect? We already talked about being partly a photon and partly an electron, or that is what the photoelectric effect is about. So let's say we have a piece of metal like this. Okay, that's our piece of metal. Could be any kind of metal. And inside of that metal is electrons. So I'll just put a couple electrons in there. Put 4 electrons in there for now. So when light comes and hits the metal, I'll make a little better waves here. Boom, boom. What happens is these electrons here are liberated, okay? So these electrons jump off. So they thought that all wavelengths of light would make an electron fly off. So it could be a wavelength. I'm going to draw another one here, just down here. Okay, it could be a wavelength like this with a really small wavelength, or it could be really long wavelengths of light. But what they found was that only certain wavelengths were able to liberate electrons, and that did not fit with the theory. So everybody thought, hey, light travels as waves. If light travels as waves, all wavelengths should be able to liberate an electron. But that did not happen. So Albert Einstein came around. Let's see if I can draw him for you. He kind of looks like this. And he's got a nice little mustache. So Albert Einstein said, from observing the photoelectric effect, that light does not just move as a wave, but it also moves as a particle, and we call that wave-particle duality. So they tested this theory out, and they had light from, so I'm going to draw 2 pieces of metal again. So on this one, they tried really low wavelengths of light, and they shot these a whole bunch, as much light as they could, with really long wavelengths. And no matter how hard they tried, or how much light they put on there, at this wavelength, they could not get this electron off the page. This electron was staying right here. And then they shone just one single tiny little photon at it at a certain wavelength, and they were able to get this electron to jump off. Okay, so this electron's gone now. So they had to figure out why that was occurring. Now, what we know now, this is part of the wave theory, okay? So I'm going to put that over here. This is the wave theory. That all wavelengths of light should pop it off, but we found that to be... So when Einstein found the wave theory to be incorrect, this is when he proposed wave-particle duality. Alrighty, so I'm going to go on a little side tangent here to teach you a little about waves, and wavelength and frequency, because I think it'll help you to understand just this whole concept a little bit better. And so the weird looking F right there, that is the frequency. So I'll write that up here, the frequency. This is the speed of light, and this is the wavelength. Okay, so we say that frequency and wavelength are inversely proportional. That's because the speed of light does not change. C does not change. So that means when frequency goes up, that means wavelength must go down. Okay, so an easy way to think about this would be, let's say that speed of light is 10 divided by 5 equals 2, right? We can't change this. What happens if the 5 goes lower? Let's say the 5 changes to a 2. 10 divided by 2 equals 5. So when this number gets lower, this number gets higher. And that's how frequency and wavelength are inversely proportional. That's how they are related together. Okay, so now that we've gone on that little sine tangent, I'm going to bring it back to the photoelectric effect, okay? So we're going to go down here a little bit further. I'm going to give myself a little more space. There we go. So I'm going to draw you a little graph here. Is that on the page? Yes, it is. So down here is going to be the frequency of the wave of light that we just talked about. And over here is going to be the kinetic energy of the electron. So I'll just put the little e for the electron there. Hopefully that makes sense to you. So now, what they found was that really low frequencies of light, there was no kinetic energy in the electron. Or basically, in our little metal, it was unable to jump off. But as the frequency got higher, it started to go up like this. So if we just kind of extend this out, it would look something like that, right? So basically they found that for an electron to jump off the page, like we were talking about back a while ago, for it to be liberated off of the metal, it had to meet this energy right here. So for an electron to be liberated and to jump off the metal like we were talking about, the photon has to have the necessary amount of energy, or the amount of energy I've got on the paper right there, to be liberated. So we know that energy, or I'll show you here in a second, how energy and wavelength and frequency are all connected together. They're all jumbled in together, and I'll show you that right here. So energy and frequency and wavelength are all connected, and here's the equation that I can show you, the simplest one. So E, this here stands for the energy of the photon. The H is a constant, just kind of like what we were looking at before with light, but H is Planck's constant, and the weird looking F, again, that is the frequency. So just kind of like before, energy and frequency this time are proportional. So if you make frequency higher, if you raise the frequency, you get higher energy. Therefore, if you go with a shorter wavelength, you get higher energy. Okay. Now this is super important for the particle-wave duality, because it tells us that only photons of certain frequency and of certain wavelength have the energy to release these electrons from the metals, and that is what the photoelectric effect is, and that's why we do these tests. Okay, so there's three main takeaways from the photoelectric effect. The first one was that not all wavelengths release electrons. That is how Einstein came up with a theory, or helped develop the theory. The second one is that more intense light, so it doesn't matter how much light you shine, if you don't have the right wavelength, you're not going to be able to release electrons from the metal. And the third one that they found was that higher frequencies release the electrons at higher kinetic energies. These were the three main findings from the theory are the three main things that we can learn, and that helped develop the theory of wave-particle duality. Thank you very much for watching.